Hey everyone, this is Andrew from Egypt and this is my matrix library demo. Okay, first let's build and test a bunch of functions. Okay, the first one is the null space. Null space is one of the four fundamental subspaces. Uh, it is the calculations for the four fundamental subspaces is one of the features of the library. And here let's see what's going to happen. Okay, so matrix A, this is the matrix A, it's a randomly generated matrix, it's a 10 by 21, and here is the null space of A. You could argue that this is wrong, I mean, who knows? Well, the test is simple. We multiply the matrix A by the null space if it produces the zeros matrix, and this is the function to check if it's a zero matrix. Okay, it returns a boolean of yes or no, and as you can see it is indeed true. This is indeed 0. Here we multiply the matrix by its null space, we store it in NS. It produces the zeros matrix. You can filter a matrix by the filter function from very small values like 10 to the minus 16, something like that. And here we're displaying the matrix. As you can see, it's a bunch of zeros, so the null space works. The left null space. Left null space is roughly the same idea, but we get a matrix. But when you multiply this matrix from the left by A, you get the zeros matrix. As you can see, this is the test. We take the transpose for the matrix to have a I'm sorry, that's the train. Okay, for a matrix to have a row space, a left null space, the number of rows must exceed the number of pivots. And since this is a randomly generated matrix, so we probably have 10 pivots. So that's why we take the transpose, so that it would be 20 by 10 matrix. Okay. So we get the null for the row space or the left null space. We multiply it by the matrix, as you can see it's from the left, and then let's see if it's the zeros matrix. As you can see that yes, it is indeed the zeros matrix, and if you filter and display, it's going to be again a bunch of zeros. Okay, so the column basis for the column space, this matrix returns the column space of the matrix A. The column space is pretty simple. These are the columns containing the pivots. Okay, as you can see, these are the first 10 columns of the matrix A, since as I've told you before, that since these columns are probably independent, so you have 10 pivots by default. Okay, so this is the column space. The row space of A, we just get the for it. We just put the non-zero rows of the row reduced echelon form of the matrix. As you can see, this is here the basis for the row space or the row space itself. And then we check using the RREF function if they are equal, and you can see that they are equal indeed. Okay. For the RREF, to make sure that it is working, well, you have to trust me, or you don't. We already tested the null space, and in the null space we used RREF to calculate it. So since the null space is working by this logic, the RREF is working, and Gaussian elimination by this logic is working as well. Okay, so let's see the compression. This is a matrix 1500 by 1000. Okay, randomly generated matrix. It's called CompTest. Okay, we perform the Gaussian elimination using the function Gauss down. We return the upper triangular matrix in CompTest. So the the expected size is supposed to be 1.5 million. Actually, it's not. It's 500,000. Why is that? In the compression or in Gauss down, after we perform the elimination correctly, we just perform some kind of compression. So the compression there are compression functions in the matrix. I would encourage you to check them out. There are some of them. I've probably closed the terminal by mistake. So these are some of the functions for compression. As you can see, this is for the upper triangular matrix. This is for the lower triangular matrix. We don't use those actually. We use the function called compress. The compress function. Okay, let's spell it again. But yeah, the terminal is closed. As you can see, this is some new results, and they are again correct. Okay, so yeah, we just in the compression function or the compress, we extract the features using a function called fill features. I would encourage you to check it out. It's green. It's green. Yeah. Okay. So we extract the features from the functions efficiently, and then we fill a variable called matrix type. It's in the matrix object. Okay, and based on that, we do some switching. We check what is the type of the matrix, and then you compress it accordingly. Okay, let's not get too technical. Okay, so the get size returns the allocated size for the memory in the heap. As you can see, it's only 500,500. Okay, so yeah, the compression works just fine. And how do you know it's working? Actually, in sorry, in the row reduced digital form or the null space functions like that, we use Gaussian elimination, and Gaussian elimination we return a compressed matrix, and since the results are correct, so the compression worked just fine and nothing went wrong. Okay, for second feature is the Fourier stuff. So first let's stop. Right, I actually wrote that wrong. Oh boy. Okay, let's see. So the Fourier transform. Fourier has a matrix. There is a matrix called DFT or discrete Fourier that performs the discrete Fourier transform for us. If you multiply this matrix by a vector. Okay. Let's first talk about Fourier mat. Okay, Fourier mat is a function that returns the Fourier matrix. It's a square matrix with this size, like it's an 8 by 8 matrix, and then yeah. Okay, so here we store it in F8, and C is a randomly generated matrix. Okay, so first you can check out how if this is correct or wrong. It's in Wikipedia actually. The 8 by 8 one, this is each element here is the complex conjugate of the one in Wikipedia, since the one in Wikipedia is in the clockwise direction, and this is in the counter-clockwise direction, or vice versa. Okay. So here we multiply F8 by C. As you can see here, we're performing the discrete Fourier transform for this matrix, and we check if it's equal to the fast Fourier transform for C. I would encourage you to check it out. Let's see, are they equal? Yes, they are equal. Okay, since they are equal, here's for fun test. This is a matrix mat tool. It's a 1024 by 1024 randomly generated matrix. We perform the Gaussian, not Gauss. We perform for fast Fourier transform for it, and here we just measure the time that the algorithm took. It only took 5 seconds. If you check it out on MATLAB, it would take a fraction of a second, which yeah, it is soul crushing, but it is what it is. So yeah, that's that's the demo. Hope you guys have had fun. The motivation for the project, I wanted to record my journey stepping into machine learning via the creation of two projects. One of them being the matrix library. As you can see, it's finished. You can check it out. I will put the link for the source code for my GitHub, or the link for the project on my GitHub. Anyway, and so yeah, via creation of two projects. One of them is the matrix library, and the other one is in the future will be a file for probability and statistics. Okay, so in this library you would find roughly 99% of the things I've learned on the MIT OpenCourseware linear algebra course for Gilbert Strang. You can check out the functions, you can test it for yourself. It's not perfect, but I love it. So yeah, hope you guys have had fun. Bye.